Today we're going to talk about free body diagrams, which is one of the most useful ways of looking at a situation where you've got objects interacting, applying forces to each other. And because what a mechanical engineer or civil engineer or whatever wants to know is, what are the forces on my materials? Are my materials strong enough to withstand those forces? How are those objects going to move under the influence of those forces? So now we're just going to scratch the surface here. We're just going to scratch the surface, and these diagrams become very sophisticated, and the study of the kinematics of an object under the influence of forces is very, very complicated. You'll take if you're a mechanical engineer, you'll take like 2 semesters just in kinematics, how things move based on this. So anyway, first thing I want to do is review what we did last week with Newton's second law. Then I want to discuss Newton's third law. And then from the Newton's third law, we come up with what are called interaction diagrams. And then we'll get to free body diagrams, and I'll do a couple of examples. And then I have some problems for you to work, which will hopefully allow you to draw free body diagrams and actually use them. Okay, so let's begin with the review. And all we said last week, we almost defined what a force is. A force is some kind of interaction that can cause, if it's the only force acting on an object, can cause that object to accelerate. That is, change its motion, change its velocity, change the way it's moving. If an object has no net force acting on it, it won't change its motion. If you go out into space, away from all planets and stars, and you throw a baseball, that baseball will keep going with a constant speed and a constant direction forever. It will not change its motion because there is no force applied to it. Now, if it comes near a massive object, there's a force of gravity. If it smashes into an asteroid, there's contact forces, and so on. And that can cause the object to accelerate. How much acceleration you get depends on the mass. So, and then we said, so this is the F equals ma, force equals mass times acceleration. And we call the force that causes the acceleration the net force equals ma. And you'll often hear me say, may the net force be with you. Because it doesn't matter if the force is with you. You might have other forces with you too that are all canceling out. What you want with you is the net force. And what I mean by that is, suppose I have a massive object. Maybe it has a mass of 2 kilograms. And maybe somebody's pulling on it with the force of 20 newtons in this direction. And maybe somebody's pulling on it in this direction with 10 newtons of force. Okay. Yeah, 30 newtons. Yeah, smart guy over there. All right, so, no, it's not a total of 30 newtons. That is a disgrace. No, because they're pulling in opposite directions. And so I think it's pretty obvious to see, let me pick a different number. Because 20 minus 10 is 10. Let's pick, let's make this 15 newtons. 15 newtons, okay? So if you pull this way with 20 newtons and this direction with 15 newtons, what's the net force acting on this object? 5 newtons. Okay, so you get the net force when you let all the other forces cancel out. Now, when you take a physics class, I don't think we're going to do it in here, but if you get in a physics class, you might have an object, and it's got a force at an angle like this, and it's got another force like this, and it might have, something like this, and you'll have multiple forces acting on it, and you have to get down to the net force. You have to figure out what that is, and there's a whole mathematics of adding vectors together. We'll probably cover that later on. But for right now, I think it's pretty easy to see that if you pull to the right with 20 newtons, pull to the left with 15 newtons, you're really the result of what you're doing, the net effect is to pull on this with 5 newtons of force. So that's my net force. And so if this object has a mass of 2 kilograms, well, I said, net force equals mass times acceleration. So if we have a net force of 5 newtons equals, and this has a mass of 2 kilograms, what's the acceleration going to be in this situation? Well, solve for the acceleration. The acceleration is equal to the 5 newtons of force divided by the 2 kilograms of mass. Yes? I mean, that's just arithmetic. Little algebra 1 there. Well, what is 5 divided by 2? Okay. And then now, here's something that many of you have seen, many of you have not seen, and I want to really show it to you. What was the definition of a newton? A newton is a conglomeration. By definition, it's other units kludged together. We defined a newton to be a kilogram times a meter per second squared. That was the definition of a newton. So this is, instead of 2.5 newtons per kilogram, I can say 2.5 kilogram meters per second squared. That's what a newton is, divided by kilograms. And I know some of you are in chemistry right now, and you are going to learn how to do unit conversions, and you know how to manipulate units and cancel them out. That is the most useful thing you're going to learn in chemistry, unless you become a chemical engineer. So I'm serious. You learning how to cancel units out and do unit conversions, you'll use that for the rest of your life, even if you don't go into the sciences or anything. Just recipes or whatever, or figuring stuff out using different kinds of measurement. So the kilograms cancel. What is a kilogram divided by a kilogram? 1. That's what we mean by canceling. When something is divided by itself, you get 1. And 1 times anything is that anything. Well, this is 1 times meter per second squared, and so we get 2.5 meters per second squared, okay, as my acceleration. So here, even though this is a review, we can kind of see how looking at the forces acting on an object, I can make a prediction about how the motion of that object is going to change over time. This object, if I do this, and these are the only forces acting, this object is going to increase its speed to the right at a rate of 2.5 meters per second every second. Now that's a useful thing to know if you're designing a machine. You want to look at the forces acting on it. Okay. So now let's talk about Newton's third law. And by the way, if I go off screen, let me know, because this is, so Newton's third law. Okay, 100 years ago, there were 3 really popular sports. 3 professional sports that everybody was into. One of them was baseball. The other one was horse racing. It wasn't basketball, it was horse racing, because you could gamble. And the third one was boxing. I don't think football, 100 years ago, football wasn't a big deal. I don't even know if it had been when it was invented, but it wasn't a big sport. But boxing, I mean, who doesn't want to watch 2, big people duke it out? Yeah, no. So, in fact, boxers were some of the first professional athletes. Because, what happens out, on a playground or out on the school ground, and 2 idiots start fighting each other, what happens? Everybody else becomes an idiot and starts running to watch the fight. Right? Everybody, even the teachers, we say we're there to break it up. We're really there to watch the fight. We want to see what happens. Now we fight with robots, right? Battle bots. That's pretty cool. So everybody loves a good fight. Well, So what they have, you had these guys that, and they said, you know, if I got this guy to fight this guy, I can have people start betting, and I can become a bookie, and I can make a little bit of money off of each bet. And so they started doing that, and then they started paying these guys. Hey, I'll pay you $20 if you fight this guy, but you have to do it in the ring, and and well, pretty soon there were some guys that started making a living doing this. Now, what do you have to do if you're going to be a fighter? The number one thing is you have to protect your hands, because let me tell you, and by the way, boxing in the old days, they didn't use gloves, right? They didn't use gloves. And in fact, boxing without gloves is actually safer than boxing with gloves, because the last thing you want to do is hit somebody with your fist in the skull. You don't want to hit somebody in the skull with your hand. Have any of you ever gotten mad and punched a wall? Go ahead and raise your hand. Raise your hand. You got mad and punched a wall? Okay. A nail. Oh my gosh. All right. Of course. Now, you think you're going to apply a force to the wall with your hand, and you do. But what does the wall do to your hand? It applies a force on your hand. And it was that force that that if you hit something really hard with your fist, the little bones, the little skinny bones, now I have skinny little hands, but if you're a boxer, I don't care if your hands are really big, you hit somebody in the skull, you can break a bone in your hand. And if you break a bone in your hand, you're done. So the early boxers, they just did body blows and maybe some slapping of the face, and that's why fights used to last a long, long time. But then they started wrapping their hands, giving themselves something to, grip, to protect their hands. And then they put gloves over their hands, and then they started putting padding on the gloves. And it really ruined the sport in a way. Because now, if somebody with a big boxing glove that protects the hand, the boxing glove doesn't protect the face of the other boxer. Who cares about the face of the other boxer? They care about their hands, because that's their bread and butter. That's how they make a living. And so now they can punch as hard as they can, and that's when they started getting knockouts in boxing. Before, people used to collapse out of exhaustion, but now they were collapsing because they had a concussion. Their brains were crushed. And then you started getting people with permanent brain damage. They called it being punch drunk. They thought it was a joke. The guys, they started talking like this after they've been boxing and lost 100 fights. And, it was very destructive. And that's all because of Newton's third law. For every force on one object, there exists an equal force on another object in the opposite direction. Now that's the way I like to explain it. Sometimes you'll see it in books or movies, like for every action there exists an equal and opposite reaction. Yeah, but people don't know it. So what I say is, for every force there exists an equal and opposite. On one object there is an equal and opposite force on another object. So when you have a fist, here's a fist hitting somebody's face. Okay. That's pretty bad. All right. There's a force, and this is the force of the fist on this person's head, the fist on the head, this is the force of the fist on the head. But then there exists an equal and opposite force, and this is the force of this person's head on their fist. And they're equal and opposite. For a force on this object, there has to be a force on this object. This is a law of nature. We observe it everywhere we look. We have never seen or observed a force on one object where there wasn't an equal and opposite force on another object. Now, usually we think of forces as being contact forces, like something is actually smashing into another force. But think about gravity. The moon circling the earth. They're not in contact. So there are forces that can reach through empty space and apply themselves. But the moon is pulled down towards the earth. The earth is pulled towards the moon with an equal and opposite force. Okay? Now, the reason they don't fall together is because they are actually moving in a circle. All right. This right here, this very simple drawing that I made here is called, this is an interaction diagram. What an interaction diagram does is it shows the force pairs. This is a pair of forces. Pair as in two, not as in the fruit. A pair of forces. We've got a force here and here, and they always go together. We've got a pair of forces. And one object on the other. Okay. Now, let's do something simple. Under this camera, I'm going to put this, I have this little wooden block, and I'm going to put this under here on the table. Now, let's see if I can tilt this camera so you can kind of get a side view of it. So here's the table, and here's this block just sitting on the table. Oh, that's kind of sideways. Do that again. And this object is under the influence of the earth and the table. Do you agree with that? Right? Gravity's trying to pull it down, and the table is holding it up. But those aren't the force pairs, the table and gravity. Let's draw an interaction diagram that shows the whole system. Just this block sitting at rest on the table. So let me draw the table. Here's the ground. And here's the block sitting on the table. So I'm going to say B stands for the wooden block. T stands for table. And E, what is E going to stand for? The earth. So now I'm going to draw an interaction diagram between these systems, these objects. This is a system. 3 different things interacting. It's called a system. First, let's do this. This is the force of gravity on the block. It's really the force of Earth on the block. Can you see that? Should I zoom in? Let me zoom in for the people in the back. What had happened? I zoomed out. Okay. Oh, come on. This is getting slower. All right. Now, what did Newton's third law say? For every force on one object, there must be an equal and opposite force on another object. Well, this is the interaction between the earth and the block. So what does the block do? The little wooden block pulls the earth up. This is the force of the block on the earth. This little wooden block is pulling up on the earth right now. Yes, it is. Well, how come we don't see the Earth rushing up towards it?
Because there's another block.
Because the Earth is 6 billion trillion kilograms. That's why. I think that's right. Wait. No, it's a trillion. It's 6 trillion kilograms. This is like 1/3 of a kilogram. So, yeah. But even though the Earth's mass compared to this wooden block is huge, and this is insignificant, they still apply equal and opposite forces. The forces are the same. So if you could think of, now the force is spread out through all the material in the Earth, but what we can kind of do is think of this force acting at the exact center of the Earth pulling up. But the Earth is not going to have any measurable effect under the influence of that force. We just don't see it because the Earth is so big. Okay? It is there, it's just that it's too insignificant for us to notice it. And then, now, what else is acting on this block? Well, we've got the table pushing up on it. And this is the force of the table on the block. But for every force, there's an equal and opposite force on the other object. So this is the force of the block on the table. Okay? And then, of course, you have an interaction between the table and the Earth and all that sort of thing. I'm not going to draw those because I really want to focus on the block. So the interaction diagram shows the force pairs. The force of the table on the block on the table, the force of the Earth on the block, the force of the block on the Earth. Okay, any questions on that? Sort of making sense? Okay. It's very evident in football. Okay, you run in, you smack into a guy real hard, you apply force, that person applies an equal and opposite force to you. Even if the effect of that force doesn't seem equal, the forces are equal. Like the most extreme version of this. What happens to a bug when it hits the windshield of a truck moving down the freeway? The bug, it's not a good day for the bug. Okay? The bug applies a force to the truck. The truck applies a force to the bug. Those forces are equal and opposite. Even if the result of those forces are not equal, the truck is annoyed if it notices at all, and the bug is destroyed. Okay, but the last thing that goes through a bug's mind when it hits the truck, well, other than its rear end, the last thing that goes through the mind of a bug when it hits a truck is, well, at least I'm going to apply an equal but opposite force to the truck. Okay, so think about that. Now what I'm going to do, I'm going to go from the interaction diagram to the free body diagram. So let's draw the free body diagram. Now, a free body diagram shows the forces acting on the object of interest by outside agents. Okay, what does that mean? It means I'm not going to show the forces that the block applies to other things. I'm just going to show the forces that other things apply to the block. What is the object of interest? In this case, the block. I'm going to show the forces on the block, which is really easy. Here's my wooden block. So I draw the wooden block. I don't draw anything else. And then I say, okay, I've got the force of Earth on the block. That's also called the weight. It's weight. Your weight is the force of gravity pulling you down. And you, by the way, you pull up on the force with the force equal to your weight. And then you've got the force of the table on the block. Now this force between these two surfaces is sometimes called, in physics we call it the normal force. The force that's perpendicular to the two surfaces, where you've got two surfaces pressing together. Take physics, you'll learn all about this in depth. Okay? So this is the interaction diagram. Very similar to the free body diagram, but the free body diagram is simple. Now, then I can take the free body diagram that I've drawn, and now I can apply the ideas of Newton's second law. Is this block accelerating? No. Therefore, what must be true about the net force on the block? It must be equal to 0. If the forces on this block are equal to 0, what must be true about the weight of the block and the force of the table applies to the block? They must be equal but opposite. Now what happens if this block was accelerating upwards? Okay? What if it was accelerating upwards? Like if you were in an elevator and you get into the elevator and you're holding the block in your hand, and the elevator goes from rest to an upward velocity, therefore it's accelerating up. What happens? How does the block feel? Doesn't it feel a little heavier? Have you ever been in an elevator and it starts going up, you feel a little bit heavier for a couple seconds? That's because the force of the table pushing up, or the force of my hand pushing up on the block is greater than the weight. You feel heavier. You're not heavier. You do not gain weight when you get on an elevator, when it accelerates up. You just need the force of that table to exceed the force of gravity down, or the force of the floor on your feet, because you're going to be accelerating up. Okay? And then what happens if you're accelerating down? You feel lighter, right? Remember how the elevator's going up and then it starts slowing down? So your acceleration is in a downward direction. So you must have a downward net force, which means that the force of the floor pushing up on you has to be less than your weight, and you'll feel a little bit lighter. How many of you jump when you do that? Oh yeah, we all jump. If you don't jump in an elevator, you have no soul. Okay? All right, so, yeah, well, get a soul, all right? Okay, so now I've got some rather complicated situations to show you, and let's take a look at this situation right here. And this will be the first problem you have. It'll be very similar to this. So let me zoom it out. I'll try to write bigger. Okay, so suppose you've got an object on wheels and you're going to pull on it with a force. Now, why do I put it on wheels? So yeah, when I put something on wheels, that means, hey, I'm ignoring friction. We'll talk about friction later. Okay? We're ignoring, these are pretend frictionless wheels. All right. This thing is going to accelerate to the right, isn't it? Unless somebody pulls back on it. And it doesn't matter what it is that's doing the pulling. It could be another object. Now let's call this object A and this object B. And then I'm going to have somebody pulling on this. I'll call that F sub P for pulling, a pulling force. Well, now we've got an interesting situation. So I can draw three different free body diagrams from this. Now, let's draw, well, I'll tell you what, let's draw the whole thing first. if somebody blindfolds me, and I pull this string, and I'm pulling the mass of A and the mass of B, do I notice or care or whatever that these are connected by strings? No, I can't tell. Hey, people, forces are aspects of nature. They don't really notice anything, though. They don't have personalities. They don't have a conscience or consciousness. They just pull, and if there's mass, that object will accelerate. So let's say this is 2 kilograms, and this is 3 kilograms. How much mass is being accelerated to the right by this pulling force? 5 kilograms. It doesn't care that there's a string between them. So what I can do is treat this as one object. So I'm going to treat this as one object, like that. And so what I can do is draw a free body diagram of the combined object. You can draw it as a circle. And you could say, well, here's my pulling force. So let's say given, let's say that this force is equal to 20 newtons. Well, a person could say, oh, well, this object right here is 3 kilograms and F equals ma, so this must be 20 divided by 3 acceleration, and this is 20 divided by 2. No. This is, as far as this force is concerned, these are two different, these two objects are one object. You follow? It's one object. And what mass does this one object have? 5 kilograms. And if you say, so this is 20 newtons, this is now the net force equals ma. But what is the mass? 5 kilograms times acceleration. So at what rate is this object going to accelerate? Yeah. 20 divided by 5 is 4. And a newton per kilogram is a meter per second squared. So now, by combining these objects into one mass and seeing that this is the net force. Now there are 2 other forces acting on this system, right? You got gravity here and gravity, well, 4. Gravity here, the ground pushing up on it, the ground pushing up. What's true about these forces? They're going to cancel each other out because there's no acceleration in the vertical direction. All the acceleration is horizontal. Now, here's the part, and even those of you that have had regular physics before, focus right now, because this might be a little bit new to you. Now what I can do is I can draw a free body diagram of A all by itself and B all by itself. So let's do B. So I'm going to draw a free body diagram of B. So here's B all by itself. Okay, now to be complete, I really should draw, okay, the ground is pushing up on B. This is the force of the ground. We'll call it, it's called the normal force. And then we've got gravity pulling it down, F sub G, that's the force of gravity. Let's just say that these forces cancel each other out for right now. But what do I know? To the right, I have a 20 Newton force. But what do I have over here? We know that this is 3 kilograms. If I go 20 divided by 3, I get 6.33, right? Meters per second squared. This thing is not accelerating at 6 meters per second. It's accelerating at 4. I already said that. So what do I need to do to complete this diagram? I want to get one of the newcomers, but I know. Yes. What's that? Yes, exactly right. Is everybody paying attention? right? If A has to pull B along, right? A has to pull B along, so I'm sorry, B has to pull A along, so A applies a force to B. Right? I'm trying to look at you in the eyes to make sure you're following the argument. Do you follow it? It's a little bit. See, this guy's being dragged along, so it's going to pull back like this. So this is the force of A on B. The force of A on B. Okay? You see that? Okay. So, can we figure out what this force is? Well, I know that the net force is equal to MA. So and I know what the mass is, it's 3 kilograms. And I know what the acceleration has to be, because I'm pulling on it with 20 newtons of force. I pulled 5 kilograms with 20 newtons of force. That gives me acceleration of 4 meters per second squared, or meters per second every second. So what does this give me? 3 times 4 is 12. And what is a kilogram meter per second squared called? A Newton. So that means the net force acting on this thing is 12 newtons to the right. So what does this force have to be? If this is 20 and I want 12 to the right, what does this have to be? 8 newtons to the left. So the force of A on B has to be equal to, well, we know it's 12 newtons minus the 20 newtons equals negative 8. What do I mean by negative 8 newtons? What does the negative mean?
It's pulling to the left.
Yeah, it's pulling to the left. It's pulling backwards. See, the net force is what you get when you add these together. 20 plus this equals 12, so this has to be equal to negative 8. 8 newtons to the left. Okay? So now, I can take this. And now let's draw a free body diagram of A. So here's A. This is a simple one. It's 2 kilograms. That's the mass. And what have we got? I got a string pulling it to the right. Now, what should I call that force? The force on that string, that tension force. Huh? Well, we could call it tension, and we actually will eventually. But based on the look at this force. This was the force of A pulling back on B. So what does this have to be? This is the force of B pulling A forward. For every force on one object, there must exist an equal but opposite force on another object. These are the interaction pairs. Force of A on B, force of B on A. And this is the power of physics and the free body diagram. Is that now I can predict what this force is. Well, I already know what it is. It's going to be 8 newtons, but let's prove it. F equals ma. This is the only force acting on A that isn't canceled out. Gravity and normal forces are canceling out. So the mass is 2 kilograms. And what's the acceleration? We already said from the first free body diagram that it's 4 meters per second squared. So what is mass times, what it was 2 times 4 is 8. And what's a kilogram meter per second squared? That's a Newton. To the right. Now look. So that's the force of B on A. Now finally, look. Does it bother you? Well, I think it's actually pretty clear if you really think about it. And by the way, you have to really think about these problems. You can't just plug and chug and try to use math. We do use math, but the math comes after you think. Some people get really bothered by the fact that this is negative 8 newtons and this is 8 newtons. But if you think about the interaction, like if you pull on a rope, if you're in a tug of war with somebody with a rope, the rope is pulling you in the positive direction, but you're trying to pull your friend in the negative direction. Right? So that means that it really shouldn't be all that surprising that this force, look, this force is to the left and this force is to the right. Okay? So what I've got for you, if I can find it, because I made copies and then I put it over there. I've got 3 problems I want you to work. And work them on your own time. And this is very similar to the problem I just showed you. I want you to take a look at this. Draw a free body diagram of A. Draw a free body diagram of B. And draw a free body diagram of A and B as one object. So that's just like what we did. And then, what is the acceleration of the system? What is the tension in the string between A and B? Tension is a force. What is the force in that string? Now, if you're an engineer and you know at what forces are going to be involved, this will allow you to design what kind of cable you need between these cars. Like when we haul the robot and the trailer, there's an emergency chain that links the trailer in case the hitch comes off. Well, somebody designed that chain and said, what are the forces that this thing is likely to experience based on accelerations and so on, and how strong do we need to make that chain? If you make a chain that's too strong, it's overweight and it's more expensive. If you make a chain that's too weak, yeah, you saved a lot of money in the short run, but when that thing breaks and you get sued because, bad things happen on the... So that's what engineers try to do, is try to design things that work with adequate safety margins at the lowest possible cost. So this one is just like what I did. Now this one, I made this one up, and I was kind of proud of myself. Let me zoom in on this. This one is going to be complicated. Now, there is no glue or anything between this. There is friction between this 2 kilogram and 3 kilogram. The 2 kilogram and 3 kilogram object, they will not slide. And so any force that exists that's parallel to the 2 surfaces that are in contact, those are called friction forces, like friction. And I want you to try to draw a free body diagram of this object, and this object. And then I want you to, on your free body diagram, I want you to try, and by the way, some of you will get this, especially those of you who had physics, and AP physics last year. And those of you who haven't had physics yet, you're going to struggle with this. I want you to give it a shot, and I want you to come back, get help from your peers, get help from me, and get it done. And really try to understand it. By the way, if you're taking physics for the first time this year, this is going to be great. You're going to have a much you're going to have an advantage because you've already had this stuff. And then number 3, I just threw in there, this is one of my least favorite idioms, is telling people to pull themselves up by their bootstraps. Well, I just pulled myself up by my bootstraps. I'd like to see you try. So go home, put on a pair of boots, and pull up on the straps and see if you can lift yourself off the ground. Now I want you to think about an interaction diagram and a free body diagram and see why. Why is it that you can't lift yourself up by your bootstraps? Think about it. This is actually going to be harder to explain. It's one of those things that you might inherently, kind of intuitively understand, but can you explain it? It's kind of hard to explain, but give it a shot. Any questions? Okay. That is all.